All right, let's go. Number 10. The Methuselah Star. A star older than the universe. HD 140283 is estimated to be about 14.5 billion years old. The universe itself? Around 13.8 billion. That's not a small mistake. That's a problem. According to standard cosmology, nothing can be older than the universe. Everything began at the Big Bang. Space, time, matter, all of it. So how can a star exist before time itself had fully unfolded? HD 140283 is extremely metal-poor. In astronomy, metals mean anything heavier than hydrogen and helium. The early universe had almost none of them. That suggests this star formed very, very early, maybe just a few 100 million years after the Big Bang. But age calculations based on its brightness, temperature, and distance keep pushing it to a number that slightly overshoots the universe's age. It shouldn't happen. Either our measurement of the star is off, or our measurement of the universe is off, or our understanding of early star formation is incomplete. And when something challenges the age of everything, that's not just a glitch. That's unsettling. Number 9. Quasars in the early universe. Supermassive black holes, billions of times the mass of the Sun, existing when the universe was less than a billion years old. That shouldn't be possible. Black holes grow by eating matter, even at maximum theoretical growth rates, limited by radiation pressure and physics itself. Building a billion solar mass monster takes time. A lot of time, but telescopes have observed quasars at redshifts greater than 7. That means we're seeing them as they existed when the universe was only about 700 million years old. Yet there they are, fully grown, fully active, blazing brighter than entire galaxies. To get that big, that fast, something strange must have happened. Maybe they formed from massive direct collapse gas clouds. Maybe early black holes merged rapidly in dense environments. Or maybe something about black hole growth in the early universe is fundamentally different from what we think. Because by the rules we know, they shouldn't have had enough time. Number 8. Ultramassive galaxy clusters. Galaxy clusters are the largest gravitationally bound structures in the universe. They take billions of years to form. Gravity slowly pulls galaxies together. Dark matter scaffolding builds the framework. Gas falls in. Structures grow. It's gradual, predictable, except sometimes it isn't. Astronomers have found enormous galaxy clusters forming far earlier than simulations predict. Some appear almost fully assembled when the universe was only a few billion years old. Too massive, too organized, too soon. According to the standard model of cosmology, structure formation should follow a certain timeline. Tiny fluctuations in the cosmic microwave background grow slowly over time. But these clusters look like they skip steps. It's as if gravity was stronger, or matter was denser, or the early universe was more efficient at building cosmic megastructures than we ever imagined. They exist, but according to our best equations, they're ahead of schedule. Number 7. The cold spot. In the cosmic microwave background, the afterglow of the Big Bang, temperature variations are tiny, just a few millionths of a degree. But there's one region colder than it should be, significantly colder. It's called the CMB cold spot. Standard inflationary models predict random fluctuations. But this one is large, smooth, unusual. Some scientists suggest it could be a supervoid, a massive empty region of space that slightly cools light passing through it. But measurements of that region don't fully explain the temperature drop. Others speculate about exotic physics, maybe a collision with another universe during cosmic inflation. That sounds extreme, but the data is stubborn. A patch of sky that doesn't quite fit. It might be a statistical fluke, or it might be a hint that our model of the early universe is incomplete. Number 6. Dark flow. Galaxy clusters should move randomly, influenced by local gravitational pulls. But measurements suggest that many clusters are drifting in the same direction, toward something we can't see. This motion is called dark flow. It implies that structures beyond our observable universe might be tugging on ours. But that creates a problem. By definition, We cannot be influenced by regions outside our observable universe. Light from those areas hasn't reached us yet. So how could their gravity affect us? Gravity moves at the speed of light. Causality matters. If dark flow is real, it suggests either measurement errors or physics we don't yet understand. Because galaxies shouldn't be migrating toward a destination we can't even observe. Number 5. Fast radio bursts. Millisecond-long pulses of radio waves. Extremely powerful, releasing as much energy in a fraction of a second as the sun does in days. They appear from distant galaxies. Random, brief, hard to predict. Some repeat, others don't. Magnetars, highly magnetized neutron stars, can explain some of them. But not all bursts fit neatly into that category. The intensity, the frequency structures, the repetition patterns. Some are too bright, too energetic, too strange. For years, we didn't even know if they were real. Now we know they are, but the mechanisms behind many of them remain uncertain. Physics allows neutron stars. Physics allows magnetic reconnection. But the exact details behind certain bursts still push theoretical limits. They exist, but they keep stretching the models. Number 4. The too big, too fast galaxies. Massive galaxies in the early universe. Compact, dense, fully formed. Observed when the universe was less than 2 billion years old. Galaxy formation models suggest a gradual buildup. Small galaxies merge. Stars form over time. Structures evolve. But some of these early galaxies look mature. Old stellar populations. High masses. Organized structures. It's like finding a fully grown adult where there should only be children. To form that many stars that quickly requires intense, efficient star formation, maybe beyond what standard feedback models allow. Supernova explosions should regulate growth. Black hole feedback should limit star formation. Yet these galaxies seem to have grown almost unchecked. Either the early universe was far more efficient, or our simulations are missing something critical. Number 3. Rogue planets. Planets without stars, floating freely through interstellar space. Billions of them. Planet formation is supposed to happen in protoplanetary disks around young stars. Gravity gathers dust. Dust forms rocks. Rocks form worlds. Stars are the anchors. But rogue planets drift alone. Some may have been ejected from their systems during chaotic gravitational interactions. That part makes sense. But the sheer number inferred from microlensing surveys suggests something more dramatic. Some estimates propose there could be more rogue planets than stars in our galaxy. That's extreme. If true, planet formation and ejection would need to be incredibly common and incredibly violent. Entire worlds wandering the dark, with no sun, no sunrise, no orbit. They exist, but their abundance challenges how we think planetary systems evolve. Number 2. The Great Attractor. Hundreds of galaxies, including our own Milky Way, are moving toward a region of space in the direction of the constellation Centaurus. Something massive is there, something gravitationally dominant, but it lies behind the plane of our galaxy, obscured by dust and stars. We can't see it directly. We infer it from motion. The Great Attractor appears to be part of an even larger structure, the Laniakea supercluster. But the mass distribution required to explain the observed velocities is enormous, and mapping it precisely is difficult. We are being pulled by something partially hidden, and while large-scale gravitational attraction is expected, the complexity and scale of these flows continue to test cosmological models. Because motion doesn't lie, galaxies don't drift without reason. Number 1. Black holes. Singularities. Points where density becomes infinite, where known physics breaks down. General relativity predicts them. Quantum mechanics struggles with them. At the center of a black hole, according to classical theory, space-time curvature becomes infinite. Infinity in physics is usually a sign that the theory is incomplete. Event horizons trap light. Time dilates. Information may be lost, or maybe not. Hawking radiation suggests black holes slowly evaporate, but that creates the information paradox. Does information disappear forever? Quantum theory says no. Classical black hole theory says maybe. Something has to give. Black holes exist. We've imaged one. We've detected their mergers through gravitational waves. They are real, but at their core, the equations fail. And when the equations fail, physics ends, and mystery begins. Those were 10 objects in space that shouldn't exist, at least not comfortably, according to our current understanding of physics. And the universe doesn't seem interested in making things comfortable. If you want more deep space mysteries like this, hit subscribe, and I'll see you in the next one.